X and Y are here jointly Gaussian random variables. I notice that they are also correlated because the correlation so they have zero mean, their variances are different, not equal, at least to start with, and they have some correlation coefficient. So that's what we start with. X and Y are jointly Gaussian random variables. We are going to define R to be the square root of x squared plus y squared, and theta is tan inverse of, let's say, y over x. So this is a classic problem. We want the joint density function of these two random variables. So the so question is, what is the PDF of R and joint PDF of R and theta, and also the marginal PDFs, etc. What is the PDF of R and what is the PDF of theta, etc. Now, this is a classic problem. If generally the way it is done is when rho is 0 or when they have equal variances, then this is Rayleigh and the phase is uniform. We will see what happens here. So notice that to start with, the joint density function of x and y is given to be 1 over 2 pi sigma squared, 1 minus rho squared, e raised to minus 1 over 2, 1 minus rho squared, x squared plus minus 2 rho xy. So this is where the difference is. We have the various sigma x, sigma y plus y squared over sigma y squared. So notice that x has variance sigma x squared, y has variance sigma y squared. Their correlation is rho. So this is a joint density function. As you can see, the inverse transformation is almost obvious. R equal to cos theta and y equal to sin theta. This will do the job because x squared plus y squared is R. Y over x is, so there is also an R here. Y over x is sin theta or cos theta, which is tan theta. So theta is tan inverse of y over x. So if you look at the Jacobian, which is easiest way here is dx over dr, dx d theta, dy dr, dy d theta. So we can just do it here. Dx over dr is cos theta, dx d theta is minus r sin theta, dy dr is sin theta. This is r cos theta. So the absolute value of the Jacobian, so first of all, the determinant is r cos squared plus r sin squared, which is simply r. So the joint density function of r and theta would turn out to be the Jacobian multiplied by the joint density function. You substitute the solutions x1, y1, where x1 is, so these are the two solutions. X1 and y1 are r cos theta and r sin theta. So if I substitute that, I'll write it here. So this will turn out to be r over 2 pi. So this is actually, here this should have, the sigmas are not the same. So this is sigma x, sigma y. So this will be sigma x, sigma y, 1 minus rho squared, e to the power minus. So here you have 2 multiplied by 1 minus rho squared. In the numerator you have r squared is common because here you have r squared cos squared, r squared sin squared, r cos theta, r sin theta. So this is r squared we can pull outside. Then you have cos squared theta divided by sigma x squared. Then minus 2 rho cos theta sin theta. So that's minus rho sin 2 theta over sigma x sigma y plus the sine squared theta over sigma y squared. This is the exponent. So I believe this is the joint density function of r and theta for r is of course positive and theta goes from minus pi to pi. Now we can find out the marginal density function of each. So to find out f or r, we need to integrate out theta, right? So this is, the whole thing is going to look like r squared multiplied by this quantity. Or we can make a little further simplification here. Let me write the cos squared theta as cos 2 theta minus 1 by 2, right? Because cos 2 theta is 2 cos squared theta. So this is plus 1. Cos 2 theta is 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. So this would be, cos squared theta is 1 plus cos 2 theta by 2, or sine squared theta is 1 minus cos 2 theta by 2. So this of course can be written as the exponent anyway. So this is r over 2 pi sigma x sigma y 1 minus rho squared. So I'm going to write it here. So f r comma theta, r theta would be e to the power minus, so multiplied by, I'm going to write it here, e raised to minus. Notice that you have 1 over sigma x squared, 1 over sigma y squared. So that's going to be 1 over sigma x squared plus 1 over sigma y squared multiplied by r squared divided by 2. So this is divided by 2. This is just due to the constant terms. Then the other terms are plus 1 over sigma x squared minus 1 over sigma y squared multiplied by cos 2 theta divided by 2. And then you have minus rho sine 2 theta divided by sigma x sigma y. And the denominator is 2 multiplied by 1 minus rho squared. So let me carry over this here. So f r theta, r comma theta equals r divided by 2 pi sigma x sigma y 1 minus rho squared multiplied by, notice that this term is only depends on r, so we are going to pull this out. So e raised to minus 1 over sigma x squared plus 1 over sigma y squared multiplied by r squared by 4, right, multiplied by 1 minus rho squared. So here you have r squared, here you have 4 multiplied by 1 minus rho squared, multiplied by another exponential term. It's 1 over 4, 1 minus rho squared, and on the numerator you have 1 over sigma x squared minus 1 over sigma y squared, cos 2 theta minus rho sine theta divided by sigma x, sigma y. So notice that the numerator can be written as cos sine 2 theta. So of course this can be written as just the numerator alone. In other words, if you take 1 over sigma x squared minus 1 over sigma y squared multiplied by cos 2 theta minus rho sine theta because this is standard procedure, so you expand this, you get cos 2 theta cos 2 theta so if it is cos, I guess it will be plus, because cos 2 theta cos phi naught minus sin 2 theta sin phi naught. So you can get the values of a and phi naught, right? So for example, phi naught will be tan inverse of b over a, which is rho sigma x sigma y 1 minus sigma x squared minus sigma y squared, and a would be square root of rho over sigma x sigma y, square of this plus this. So 1 over sigma x squared plus minus 1 over sigma y squared. So consequently this becomes r divided by 2 pi sigma x sigma y multiplied by 1 minus rho squared e to the power minus 1 over sigma x squared minus sigma y squared over r squared over 4 1 minus rho squared and e raised to minus a cos 2 theta plus phi naught over 4 multiplied by 1 minus rho squared, where a and phi naught are given by these terms. I believe because we brought this 4 common term there will be a 2 here, which means there will be a 2 here and there will be a 2 here. So now using this expression, it's very easy to find the FR theta. So FR and F theta. So FRR is, for example, integral of FR theta R theta over d theta goes from minus pi to pi. So that's all the constants, all the terms other than the theta I pull outside. So you have sigma x, sigma y, 1 minus rho squared. I believe we are missing a square root factor here. There is this denominator is 1 to the power half. This is 1 half. So here you have 1 half just on this term. So this is 1 half, which is the same as a square root here. So this is under the square root, or 1 half. Then you have e raised to minus r squared over, or 1 over 4, 1 minus rho squared. Here 1 over sigma x squared minus 1 over sigma y squared r squared multiplied by minus pi to pi this term e raised to minus so it essentially looks like e raised to minus b cos so b cos 2 theta plus phi naught d phi. But this is the expression for I naught of b. So bottom line is, so this is the Bessel function of 0th order. And so if I substitute for that, so where b is of course, b is this quantity, anything other than, so b is capital A divided by 4 multiplied by 1 minus rho squared. And I believe when we expand it, remember there is, if you look here, this r squared multiplies, multiplies all the terms. So of course r squared, there will be an r squared here also. So we took care of the r squared here. So there is an r squared here. So there is an r squared. So b is this. And if theta is very easy, I believe to find out f theta, it is easier to use this original expression. So remember, this is also the joint density function between r and theta. So if I call, let me call this whole quantity to be, some, let's say u, or some constant k. Then because we just need to integrate out r. So I'm going to call r squared k to be x, or u rather. So we have 2r dr multiplied by, so 2r dr multiplied by k equal to du. So if you want to figure out f theta, theta would be integral 0 to infinity f r comma theta r theta dr. So this is 1 over 2 pi sigma x sigma y 1 minus rho squared to the power half. Then you have integral 0 to infinity. The limits for u are the same. So r squared k is, the exponent is simply u, e raised to minus u. So notice that r dr, you have r here. So when you integrate this, you have, you're integrating this side. So r dr is going to be, du divided by 2 dk, which is what I'm going to substitute here. So 2 du divided by 2 dk, 2k. So k is going to be that whole thing. So that 2k goes outside. Then this integral e raised to, integral 0 to infinity e raised to minus e du is 1. So the answer is 1 over 4 pi sigma x sigma y square root of 1 minus rho squared multiplied by k. So let me substitute for k from there. So this is 1 over 4 pi sigma x sigma y 1 minus rho squared. This is within the square root. K is going to be, the numerator is, K is in the denominator, so the numerator is 1 minus rho squared, and the denominator is cos squared. So you can see there, cos squared, the last board, cos squared theta over sigma x squared minus rho sine 2 theta over sigma x sigma y plus sine squared theta over sigma y squared. So some minor cancellations happen. This cancels with this, so we would only lose, so here we would have 4 pi sigma x sigma y, and here you would have square root of 1 minus rho squared. 1, 2 cancels. If the 2 cancels with the 4 here, and so this is the result. Now let's do some special cases. So obviously r and theta are not independent. You can clearly see, because if you take the product, you are not going to get the joint density function we had. But suppose now sigma x, so the special cases are, assume sigma x equal to sigma y, or the first thing is sigma x equal to sigma y. Then notice that this will turn out to be, and we can also take rho to be 0. So this is the classic case. That is, x and y are independent and they have equal variance. Then this will turn out to be simply Rayleigh, because this was here plus, right? This is plus here. So sigma x squared and sigma y squared are equal. So this will be 1 over, this will be 2 over sigma squared. 2 cancels with this here. 4, here you have 2 multiplied by 1 minus rho squared r squared. This is identity, because rho is going to be 0. If rho is 0, this will turn out, this will simply integrate out to 1. The rho is 0, so phi naught is 0, and b is going to be right, because rho is 0, the two variances are equal, so a is 0, so this term is just 1. So here you have e raised to minus r squared over 2 multiplied by 1 minus rho squared, and here r, that's the classic Rayleigh. So if sigma x equal to sigma y and rho is 0, then f r r reduces to the classic equation, r over and this will integrate to 2 pi, because this will be 1, so the 2 pi goes away. You have sigma squared, so rho is 1, so e raised to minus r squared over 2 sigma squared r positive, right? You can put a 2 pi here, so this 2 pi goes away. So that's the special case, and at that time, look at theta. Theta will be, rho is 0, sigma x squared and sigma y squared are 1, so that's going to be 1, which is rho is 0, so this will turn out to be 1 over 2 pi, or uniform, and the product is equal to the joint density function. So the moral of the story is, when the two variances are equal and the correlation coefficient is 0, that means x and y are independent, then the magnitude and phase are also independent. The magnitude is Rayleigh, we just showed there, and the phase is uniform. All other cases, they are dependent. And you can do another special case. Assume sigma x equal to sigma y equal to sigma, but rho is not 0. So if these two are equal, this will become 1. Rho is not 0. So this will be, so in that case, f theta theta, for example, becomes square root of 1 minus rho squared over 2 pi. Notice that this is sigma squared, this is sigma squared, this is sigma squared, this is sigma squared. So sigma squared cancels. Cos squared plus sine squared is 1. So this expression becomes 1 minus rho sine 2 theta. Again, another classic expression, theta less than pi, minus pi to pi. And what happens to r is you just have to do it here. So rho is 0, and rho is not 0, but this term is 0. So a is going to be, I guess this is rho squared. So a is going to be, in that case, 2 rho over sigma x sigma y. And you have to substitute it. You have to substitute it here. So b would turn out to be, so this would be I naught of 2 rho r squared over 4 multiplied by 1 minus rho squared. So FRR in this case is going to be not Rayleigh, but so notice that we are considering the case sigma x squared equal to sigma y squared. So this is sigma squared. R over sigma squared, you have this quantity. So if I simplify all that, this will turn out to be and numerator is r e raised to minus r squared over 2 sigma squared, I believe, because also there is a 1 minus rho squared here in the denominator. And then you have this I naught function, Bessel function, which, so it's a bit of mess, but it's doable. So FRR is Rayleigh-like, not exactly Rayleigh. It's actually this equivalent to the Rishian when you have a non-zero mean. So notice that in this case, when x and y are not independent, these two, the magnitude and phase are not independent. In other words, when rho is not equal to 0, the magnitude and phase are not independent. When you can put a rho equal to 0 and make the, so another case you could do is make the x and y independent. In other words, rho is 0, but do this case, sigma x is not equal to sigma y. Then again you can see that it's not, these two quantities are not independent because the phase is easier. So the phase is going to be, it's not uniform because it is 2 pi sigma x sigma y. Rho is 0, so that's 1 over cos squared plus sine squared. So everything will stay the same, the denominator, because nothing will simplify. This is 1 over cos squared theta over sigma x squared plus or minus rho sine 2 theta over sigma x sigma y plus sine squared theta over sigma y squared. And FRR is going to be similarly. FRR is a bit messier. So it's r over sigma x sigma y square root of 1 minus rho squared e raised to minus 1 over 4 1 minus rho squared 1 over sigma x squared plus 1 over sigma y squared multiplied by r squared, followed by this I naught function, I naught of b. So you just have to substitute. Remember, rho is 0. So a is going to be 1 over sigma x squared minus 1 over sigma y squared multiplied by r squared over 4. So again, Rayleigh-like, but not quite Rayleigh, because so it is Rician-like mostly. And of course, you can go on to find out the mean and variance. So the bottom line is, in all these cases, so that's the most general case. So we have the joint density function. We have each density function for R, theta, most general case. Then the very first case, which is this one, when the two variances are equal and they are x and y are uncorrelated, you get the R is Rayleigh. R is Rayleigh, and the phase is uniform, because you could see that f theta. In this case, of course, f theta would be simply 1 over 2 pi for theta less than minus pi to pi. And moreover, the joint density function is the product of the density functions. This is the next interesting case. When they are correlated but equal variance, then also it's a mess. They are dependent actually, R and theta. And same is the case when they have unequal variance, but they are x and y are independent. In that case also R and theta are dependent. So as I said, so only the case one is generally when x and y are independent and equal variance. So we are back to the case one. Then f r theta, r comma theta, is the same as f r r multiplied by f. So this is the only classic case which is generally done, and r is Rayleigh and the theta is uniform. So in that special case, the magnitude and phase are independent. The magnitude is Rayleigh, phase is uniform. Everywhere else it's a mess. So for example, x and y are independent but unequal variance. The magnitude is like this, and the phase is another mess, because the theta is all over. And if x and y are equal variance but still correlated, so here x, y are correlated. The magnitude is a mess, phase is not such a mess. Again, this is mostly looks like Rician or random variable. And the easiest case, which is classically done, is when two independent Gaussian random variables with equal variance, if you look at their magnitude, which is square root of x squared plus y squared, that's Rayleigh, and the phase tan inverse of y over x, that's uniform. And moreover, their joint density function is the product of the density functions. Consequently, magnitude and phase are independent. So that statement, magnitude and phase are independent, is very special, only applies to this very special case. Any of the assumptions are violated, even if x and y are independent, but their variances are unequal, the magnitude and phase are not independent. They are dependent, and in fact a big mess. And same thing here. Even if they are equal variance but correlated, the magnitude and phase are not independent or dependent. In the general case, when they have unequal variances and correlated, it's even a bigger mess, which is here. You have the joint density function, either that expression or this expression, and you have the marginal density function of R, and you also have the marginal density function of theta. Thank you.